Hi dear students, I hope all of you doing well. I took some gap. This is because I was out of station these days. So here onwards I will try to post my videos regularly. So please do follow and subscribe my channel. Give your valuable suggestions in the form of your comments. That encourages me a lot. And in future I will try to do the videos on competitive exams like NEET and JEE also. Okay. Here I am going to make the videos based on your textbook, NCERT textbook or your state chemistry textbook. So if you have textbooks, read your textbooks thoroughly, watch my videos and you will understand the concepts very clearly. Okay, without wasting time, let's start our today's topic. Today we are going to discuss closed packet structures. So in this topic we are going to discuss what is the pattern of arrangement of particles in crystal system. In previous lectures we have discussed different types of crystal systems. Now how the particles or spheres are arranged in crystal systems. Actually this arrangement will be in 3 dimensions, but 3-dimensional arrangement we cannot understand without knowing the 2-dimensional pattern. So let us start with the 2-dimensional arrangement. Before going to that, briefly we will discuss 1-dimensional pattern. In 1-dimensional pattern, particles are arranged in a row. Here if you observe this row, all the particles are arranged in a systematic manner, and here each sphere is in contact with the 2 other spheres. You take any sphere, this sphere, it is in contact with these 2 spheres, this sphere is in contact with these 2 spheres. So here the coordination number of each particle is 2. Coordination number is 2. What is coordination number? So one of the very important, very short answer question for your board exams. It is the number of nearest neighbor atoms. Number of nearest neighbor atoms of a particular particle or particular atom. Here if you consider this sphere, it is in contact with 2 other spheres, so its coordination number is 2. You take this sphere, it is also in contact with 2 other spheres, so its coordination number is 2. Simply in 1 dimension the coordination number is 2. Next let us move on to 2-dimensional pattern of arrangement. In 2-dimensional pattern of arrangement, here the particles are arranged in a systematic manner in different rows and vertical columns. Here these rows and vertical columns are aligned perfectly. That means all are in a particular sequence. So I will show you a model. See, observe this diagram. Similar to this, I have made a small model here. So all these particles are arranged in a systematic manner. So one particle is in contact with other particle, that particle is in contact with other particle in a row as well as in a column. Here these rows and columns are in a good alignment. And if you take any particle, say for example this middle particle which I have represented with a red sphere, and it is in contact with 4 other spheres. So let us see, 1, 2, 3, 4. This middle one is in contact with 1, 2, 3, 4. 4 particles, 1, 2, 3, 4. So the coordination number of this middle sphere is 4. So in 2-dimensional pattern of arrangement, the coordination number is 2. Here one small point I forgot to tell you. In 2-dimensional pattern of arrangement, there are 2 types of arrangement. There are 2 types of possible arrangement. One is square close packing arrangement. This one is square close packing. And second one is hexagonal close packing. In square close packing, all the spheres are in aligned. All the spheres have vertical as well as horizontal alignment. Okay, the coordination number of the particle is 4. Do remember. Next, second type of arrangement is hexagonal close packing. In hexagonal close packing, if you observe carefully, this is the first row. This is the first row spheres. Here you can observe some gaps between these spheres. These gaps between these spheres. These gaps are called depressions. depressions, and second row spheres are placed in the depressions of first row. Third row spheres are placed in the depressions of second row. Fourth row spheres are placed in the depressions of third row. So I will show you a model. See here, let us consider this one is the first row. In the first row, these spheres having some depressions, these gaps, and the second row spheres are placed in the depressions of first row, and third row spheres are placed in the depressions of second row. Understood? And if you observe carefully, there is no vertical or horizontal alignment between first row and second row. But you can observe the vertical as well as horizontal alignment between first and third row. Similarly, the second row have similar alignment with the fourth row. That means if you consider the alignment in first row as A, the alignment in second row is different. Let us consider that is B. Here arrangement is A, here the arrangement is B type. Since the alignment or arrangement of first row is very similar to third row, let us consider the third row alignment is also A type. That means these two are similar. The fourth row alignment is very similar to third row alignment, so these two are similar. So this type of arrangement is called AB type arrangement. AB type arrangement. Whereas in case of square close packing, all are having vertical as well as horizontal alignment. It is called AAA, means AA type alignment. That means in two-dimensional close packing, there are two possible arrangements. One is square close packing, in which each particle is in contact with 4 other particles, so coordination number is 4. And whereas in hexagonal close packing, each particle is in contact with the 6 other particles. See this, if you consider this particle, it is in contact with 1, 2, 3, 4, 5, 6. You can observe in this model also. If you consider any one particle, suppose if you consider this particle which is represented with blue color, it is in contact with 1, 2, 3, 4, 5, 6. So this is in contact with these 6 spheres. Okay, understood? So here the coordination number in case of hexagonal close packing is 6. Here in a hexagonal close packing, the arrangement in first row is very similar to third row, and it will be very similar to in fifth row, and so on. Means all odd type arrangements are very similar, and all even type of arrangements are very similar. So it is called AB type arrangement. Practically it was observed that only 52.4% of space is occupied due to two-dimensional square packing arrangement. Whereas in hexagonal close packing, 60.4% of space is occupied. 60.4% of space is occupied. That means it is more perfect one in comparison with square close packing. That means hexagonal close packing is more efficient than square close packing. Here one more important point we need to understand is, here you can observe some gaps between two rows. Here see, these are the gaps. These gaps are called voids. VOID, void. Voids are holes. HOLE, holes. Voids are holes. If you observe these voids are in a triangular shape. These voids are in triangular shape, like this. But in one row, the apex of these triangles showing upward direction, but in the next row, the apexes of the triangles showing in downward directions. Now let us move on to three-dimensional arrangement. In three-dimensional close packing, there are two possible arrangements again here. Here, three-dimensional close packing from two-dimensional square close packing. Three-dimensional close packing from two-dimensional square close packing, and three-dimensional close packing from two-dimensional hexagonal close packing. So let us discuss one by one. First one, three-dimensional close packing from two-dimensional square close packing. Here it's very simple. In this type of arrangement, all the particles have vertical as well as horizontal alignment. See this model, so you can easily understand. See, this is the first layer, second layer, third layer, and so on. We can make a number of layers. Here you can observe the spheres in the first layer are vertically as well as horizontally aligned with the second layer. Second layer spheres are in alignment with the third layer, and so on. That means all the particles have vertical as well as horizontal alignment. Due to this type of arrangement, we will get simple cubic or primitive cubic unit cells. Now let us discuss three-dimensional close packing from two-dimensional hexagonal close packing. Just a few minutes before, we have seen the two-dimensional close packing, two-dimensional hexagonal close packing. In two-dimensional hexagonal close packing will be like this. And here the second layer particles are placed in the depressions of first layer. Due to this we will get some gaps. Those gaps are called voids or holes, and these voids are in a triangular shape. Few triangles are pointing upwards, few triangles are pointing downwards. This we have discussed. Now let us consider this type of many layers. Now let us take first layer. If we keep second layer over the first layer in such a way that the triangular voids of first layer are covered by the spheres of second layer. Let us consider some n number of this type of layers. When second layer is placed in the depressions of first layer, then some triangular voids of first layer are covered by the spheres of second layer. Some triangular voids of first layer covered by spheres of second layer. Due to this, some type of voids are formed. Those voids are called tetrahedral voids. The tetrahedral voids will be like this. So if you observe carefully, here these three spheres making a void, triangular shape, and upon this void one sphere is placed. This sphere, which is represented with red color, it is the sphere of second layer. Now when the spheres of second layer placed over the depressions of first layer, then some of the spheres occupy trigonal voids of first layer. Due to this, tetrahedral voids will be formed. See, for example, these three are the particles or spheres of first layer. Here you can observe one void or gap. This is a triangular void. If this triangular void is occupied by the sphere of let it be sphere of second layer, occupied by the sphere of second layer, then this void is covered by this sphere. Due to this, a gap between these four spheres is called a tetrahedral void. So how a tetrahedral void will be formed? When the triangular voids of first layer occupied by the spheres of second row, then a tetrahedral void will be formed. In some cases, the triangular voids of second layer falls over the triangular voids of first layer. See, for example, let it be, these are the particles in first layer. These first layer particles making triangular voids. This is a triangular void. Okay. Now this is particles in these are the particles in second layer. These are making a triangular void. If you observe the triangular void of second layer falling over the triangular void of first layer, due to this type of arrangement, octahedral void will be formed. Here in this diagram, these are blue colored spheres represent the first layer. This represent the first layer, and this red colored spheres representing second layer. Then the triangular voids of second layer falling over the triangular voids of first layer. Due to this, an octahedral void will be formed. Now let us know how to calculate or how to know the number of octahedral voids or tetrahedral voids in a given crystal system. This is very simple. If we consider in a given crystal system, a total number of spheres will be n. In a given crystal system, a total number of spheres will be n. Then a number of octahedral voids will be n. Means number of octahedral voids is equal to number of spheres present in the crystal system. Next, number of tetrahedral voids will be equal to 2n. Means double the number of spheres. If number of spheres are n, then octahedral voids will be n and tetrahedral voids will be double, that is 2n. To remember this, I will give you a small trick here. 1n, n means 1n. Number of octahedral voids will be 1n. Octahedral starting with the letter O, O for 1. Octahedral voids will be 1, O octahedral starting with O, no? So 1n. And tetrahedral voids will be tetrahedral starting with T, no? T for 2, 2n. So like this you can remember number of octahedral voids or number of tetrahedral voids we can easily calculate from the given crystal system if you know the number of spheres. And these formulas are very important for your competitive exams. Now dear students, just now we have discussed placing second layer over first layer. When second layer is placed over first layer, there will be formation of two different types of voids, tetrahedral voids and octahedral voids as shown in the figure. Now placing third layer over second layer. Placing third layer over second layer. Here this can be done in two different ways. The first one, placing third layer over the tetrahedral voids of spheres of third layer. That means tetrahedral voids of second layer are covered by spheres of third layer. When tetrahedral voids of second layer are covered by spheres of third layer, then the pattern of arrangement will be like AB, AB, AB. That means first layer will be in alignment with third layer. That means first layer and second layer will be different, just like this. Here first layer is different, second layer is different. When first and third will be similar, third and fifth will be similar, like this. So this type of arrangement is called AB type arrangement. That means first layer is different, second layer is different, but the alignment of first layer is similar to the alignment of third layer. This type of arrangement is called AB type arrangement, and this is called hexagonal closed packet structure. How a three-dimensional hexagonal closed packet structure will be formed? When the third layer is placed over the tetrahedral voids of second layer, then we will get a HCP arrangement. Now covering octahedral voids of second layer with the spheres of third layer. Covering octahedral voids of second layer with the spheres of third layer. When the octahedral voids of second layer are covered with the spheres of third layer, then the arrangement will be different as shown in the figure. Just observe that figure. Here first layer is different, second layer is different, third layer is different. But first layer is similar to fourth layer. First layer is similar to fourth layer, second layer is similar to fifth layer, third layer is similar to sixth one. Suppose if you consider this A is 1, 2, 3, 4, 5, 6, first and fourth are similar, second and fifth are similar, third and sixth are similar. This type of arrangement is called ABC arrangement. Means first three layers have different types of arrangements, and next the same pattern will be continued. So this type of arrangement is called ABC arrangement. So this arrangement is called cubic close packed arrangement, or CCP, or face centered cubic arrangement, FCC. So cubic close packed structure or face centered cubic structures will be formed when the spheres of third layer are placed over the octahedral voids of second layer. So these are the different concepts, dear students. So let me summarize all these topics briefly, particularly three-dimensional pattern of arrangement. In three-dimensional pattern of arrangement, when we place second layer over first layer, then there will be formation of two different types of voids. One is called tetrahedral void, and how a tetrahedral void will be formed when the spheres of second layer placed over the triangular void of first layer, then a tetrahedral void will be formed, and its arrangement will be like this, and as shown in the figure. Next, how an octahedral void will be formed. An octahedral void will be formed when the triangular voids of first layer are covered by triangular voids of second layer. See, this is the triangular void of first layer, this is the triangular void of second layer. These two voids are covered. So if you see, we can observe one triangular void is falling over another void. Next, placing third layer over second layer. While placing third layer over second layer, there will be two different types of patterns. One is placing the spheres of third layer over the tetrahedral voids, then we will get a hexagonal close packing structure. When we place the spheres of third layer over the octahedral voids, then we will get a cubic close packed structures, or FCC, face centered cubic structures. Okay, I hope you understood. Just go through this topic, and here the most important topic is how to calculate the number of octahedral voids and tetrahedral voids. Just before I have given you one formula. Number of octahedral voids will be n, number of tetrahedral voids will be 2n. Okay, dear students, actually this is a very big topic. I tried to make this topic as short as possible, so I hope you understood this. And still, if you have any doubts on this, and tell me in the form of your comments, and I will try to make this topic more simpler. Okay, thank you, dear students. Thank you for watching. See you in the next video. Bye.